Hi there, welcome back. Well, one more step forward. The audio stage has been completely checked, and I'm going to just speak a bit about that and show you what I discovered. This stage has been actually quite uneventful. All capacitors were changed, and as usual, I tested a few of them, and just about all of them were completely gone. Resistors were very, very good except one, which I think was my problem. I was desoldering a capacitor from the same pin or the same connecting point, and I think I overheated that one side of the resistor, so it just fell apart, and that was replaced. But nothing too dramatic, so it went well. I want to go through what I've done, show you some of the interesting things I've found on the schematic on this particular set, and then we'll do a power-up test and see if the audio is working as it should be. You've seen some of the painting that's happened with the power supply. Now, everything that we see here, basically all of this has to do with the audio stage. And it's pretty easy to figure that out because you've got this guy over here. This is the pickup or the phono input. And if you follow that through, you get this all going through the tone controls, a little bit of the switching that's required. There's some there's a tone control there. There's the volume control. There is the capacitor that connects everything up to the audio preamp. So preamp, phase inverter, two output tubes in push-pull, transformer and speakers and output. The way I've done this, you can see that all the capacitors are in red. That means they've been changed out. So if we take the signal from point 3 over here, which I believe 3 plus 2 is TB Wiedergabe, TB, TA. Well, I can't figure out which is which. One of these is pickup in and the other one is out. Now out would be to a tape recorder. This would be more a tape input, I think. Yeah. I think this would be a tape input and tape out. I might be wrong, correct me if I'm wrong. So let's take this point number 3 here. Goes in here, goes through there. This switch over here, and someone's asked me how to explain how the switching works. If we look at this, it says 3HIK, where the center is I. Now this thing is pretty well explained. If we look at the switching diagram, we've got 3 is activated by the TA, in other words, the phono or tape input. So 3I, where is it? I, there's your number 3 coming down here, and there's your HIK. So I is over there, that's the center pin, and K and H. These things are normally drawn, it should tell us, well, it's set as off. So the way this is drawn is when it's off. So if you push TA, it flicks over between H and I. So this switch goes plump to there. Okay? So if we push pick up, we should activate or short I and H. Okay? Let's go back to where we were. So if we push TA, we know that I and H get shorted. In other words, that signal comes from there, jumps through to I, and it's now over here. Okay? The alternative would be this K. Now what would K be? Well, if this is activated by your TA switch, which is your external audio, whether it's tape or phono, I'm beginning to think they mean tape, then your K would be radio. So that means if you follow from K backwards, from this 3K backwards, you'll probably find this is all the switching for the audio from your either AM or FM. But all we're interested now is audio from our pickup. So it goes through here, over here. It goes in here, and you've got a capacitor. This is 22 nanofarads. This is actually that funny, sweet-looking one that was inside the switch box. So this is part of the audio circuit. This is actually one of the most important coupling caps in the audio circuit. And that then goes through to here. Now, there's a switch here, 1, G and F. This would short that to ground. Why would it short it to ground? Well, let's go look at the switch diagram again. So 1, F and G. F and G means it's shorted. Now, why would that be the case? Well, when you switch on, remember this is off. So when it's off, F and G is shorted. F and G shorted means that all your audio supposedly going into your audio amp, into the preamp and then the power stage, is shorted to ground. So there's no audio. Well, the only reason they have this is so that when you switch off your radio, it shorts it to ground so that you don't get any noise after you've switched off. Makes perfect sense. A lot of these radios, when you click the power off, it still goes and makes some noise for a while. It tries to play for a while because the capacitors are charged and there's audio in the line and there's nothing shorting it to ground. So all this is here for is when you switch off, it immediately shorts the audio to ground, so it cuts out the audio to the power amp. And it means that all the voltage or the current, the power that's still in the capacitors, the power amp will still work, but there's no audio coming in. So this is a mute switch when on power off. Quite clever. So provided our audio has not been muted, in other words, the power is on, this switch is open, so the audio is there. And now it goes into here. But before it gets to this resistor, it sees this. And this is it's an RC network, which basically lets you drain, it'll drain highs to ground. So high frequencies are the only things that can get through a capacitor. And the lower the capacitor, the smaller the capacitor, the higher the frequency has to be to get in, right? And then just to help that, if you've got yourself a potentiometer or a variable resistor to ground, it also adjusts the amount or the level at which the frequencies get drained to ground. But you've got something else here. And this is where these circuits are quite interesting, because all this here has to do with tone shaping. Because as you see, you then get signal going through this resistor, and it's here, and there's another capacitor there, and that capacitor gets shorted to ground as well. Or rather, that capacitor gets, well, tuned to ground. If you move this to 0, that whole capacitor is shorted to ground. So a lot of the highs get drained to ground, so you get a more bass-rich signal, or less highs. But at the same time, you've got your signal keeps coming, it keeps trying to get through here, and it gets through here to the top of your volume pot. But before it gets through here, through this capacitor, there is a resistor, a variable resistor over here, which is actually the bass control, because this is high frequencies going through your 180 picofarad capacitor. So if you give it a DC path, albeit at a high resistance, you are basically annulling the effect of this capacitor, so you're letting high frequency or low frequencies get through as well. So this is your bass control. Anyway, then it all gets to the top of your volume pot. And you'd think, that's it now, right? Now you've got the wiper, and it buggers off into the preamp. Well, not quite, because what these pots have is tappings at certain points on their rotation, right? And the reason you have that is so that you can get different effects at different volume levels. It's almost like a loudness control. Because if you've got a loudness control, what they're trying to do is give you a stronger, a more a more bass-rich sound at lower volumes, which normally you wouldn't get because the effect of the resistance. As you get away from this point here, down, that resistance is high, and you've got a capacitor, so you're creating a high-pass filter. So you've got to compensate that with a different path to annul some of that effect or to enrich some of that effect. This whole thing is actually more complicated than I've cared to analyze. And you see it in a lot of different radios, especially German radios. I can't speak for the others, but I've seen it in a lot of German radios. And some of the switching over here would be things like orchestra. In fact, one of these will be bass and the other one will be treble probably, or orchestra. And I'm not sure what these switches are actually, 11, 12. I think it's probably the orchestra and what is it, jazz switch. These here, 5C, 5-4, can't read that letter. This would be again one of the switching, the tonal switching. So everything down here is to give you different tonal compositions for your sound that will finally get through this capacitor here. Now this capacitor here is really the coupling between all this tonal and volume control and your preamp. And now you're at the preamp proper. So what exactly happens here? Well, signal's coming in, it's meeting a triode. It's half of the ECC83. This triode is biased with a cathode resistor of 150 ohms. Let's forget about that other line that goes off that way for now. So that's biased with that resistor. So it's a normal cathode biased triode, which means that whatever signal goes in here gets amplified up to here. And that comes out and goes through this capacitor into that valve, which will then amplify it. And it'll amplify it and push that amplified signal through that half of the output transformer. I suppose that's the simplest way of looking at it. That is the load for that triode, or that pentode, beg your pardon. But there's more than that. The signal that comes in here has got all the frequencies so far that you've allowed through. So it goes in here and it would be amplified practically sort of flat for the audio band. However, there's this thing down here that comes back from the output transformer. And this is a feedback that tone shapes again what your signal is going to sound like. This is full of tone shaping. Makes sense, all right? Now what happens here is you've got a bias voltage over here. The current flowing through this tube or this triode through that resistor to ground creates a voltage there. Let's call it 5 volts. Okay? If that is 5 volts, that there on the grid is 0 volts because it's got this ground reference resistor. About 0 volts. And that means that there's a negative voltage reference to the grid. So it's grid voltage minus cathode voltage. So 0 minus 5 gives you minus 5 volts. And that minus 5 volts is the bias on that tube. That is what is shutting down this tube from passing all the current you want. It sets it into the active region. Okay? Now, if that stayed at 5 volts, that's what would happen. Whatever came in here gets amplified and pushed through there. However, whatever's being pushed through there and ultimately through the transformer and through the speaker is being fed off, a little bit of that is being fed off through here and back to that point. And what's happening here? Well, there's an inversion that happens in here, and that means that whatever comes back from the speaker is being subtracted from the signal. It's the inverse of the signal that you want to get through. So it's subtracting from the bias point. It's modulating that DC voltage. So what you've got here is an DC voltage with a AC component, which is that feedback or fed back part of the output. And what is that fed back part of the output? Well, depending on what the switching that happens here is, it's either more highs or more lows. Okay, that's basically what it is. Signal comes in here, gets through this resistor, meets this capacitor with a resistor to ground. Okay, that's fine. It loses a bit of the high frequencies because it leaks through to ground. Now what happens if you switch that thing in there? Well, 10 and 11, if you look at the switching diagram, is actually the orchestra or jazz switch. If you short that, that means that that resistor becomes 0. It's a short to ground, which means more of the highs come down. If you lose more of the highs and the rest goes through there, it means that the highs aren't going to be affected. The high frequencies aren't going to modulate this bias because you've got rid of that as from your feedback signal. All right, let's assume you get some of it through there, gets through this resistor and it meets this capacitor. What happens here? Well, capacitor normally just allows high frequencies through. So you've stopped the bass from going through. So high frequencies go through and act on the feedback. No low frequencies, right? Well, not many. What happens if you short that out? You're basically making this stop having the effect on the low frequencies. So the low frequencies get through and also modulate and also affect the component of the sound that's going to get amplified. So basically you are giving it two options here. The one option, the basic option, is also with any feedback it reduces distortion. But because you're tapering which frequencies get through that feedback loop, you're also giving it a tonal influence, right? And finally, your signal is here. And finally, it's gone through and modulate and driven this tube, and it's got a grid stop resistor there, no big deal. It's driven this tube and boom, it goes through and it drives that half of that transformer. But what about this half? What about this guy? What's it doing? And where is it getting its signal from? And what signal should it get? Well, in a push-pull, you want this tube to do the exact opposite of that one. So you want the signal here to be the exact opposite of that one. How do you get that? Well, the way you get that is through something called a paraphase phase inverter. And that is by taking some of the signal that's going to drive that tube, right? You take it from there, and there's a voltage divider here. That's a 470. That's 1.2 meg. You take it from there, and you feed it back into the grid of that half of the tube. In other words, of the other triode. And this triode is biased differently. It's biased with a very big resistor to ground, which is grid leak bias. It's automatic bias, I think it's called. And it just means that a proportion of the signal that's going into there is being fed through here and gets amplified again. And it gets amplified so that the signal that comes out of its anode is back up to where that one is. So signal here is the same level as that one, but because it's gone through another triode, it's inverted. It's 180 degrees phase inversion. So if this signal, if you've got a sine wave going up there, at the same time you'll have a sine wave going down there. And that feeds this driver, or this pentode, which drives that half of the transformer, and that's how you get push-pull. I'm wondering if that makes any sense. It makes sense to me. Okay, I think you might have to be a little bit mad to understand this, but it makes sense to me. That's how it works. And something I've got to say here now, and that basically is it. That's your amplifier. But there's something I've got to say here, and you've got to go and see this. There's a website called valvewizard.co.uk. If you haven't been there, you should. It's run by a gentleman called Merlin Blenko, I guess hence the wizard part. And he really is a wizard with tube stuff. And I know it seems that his favorite stuff is guitar gear, valve-driven guitar gear. But the descriptions he gives on the type of power supplies, the type of output stages, the type of preamp stages, there are articles on each type of each building block part of a tube amplifier that are really important reading. It gives you the different type of phase inverters. You'll get explained how to design an output stage, a complete output stage, whether it's class A or class or push-pull. It goes through the calculations. It really is an amazing website, and you should really see it. It really is great. That's basically it. And one more thing I want to tell you. This tube, this ELL80, everybody's been commenting about how expensive they are. Yes, they are expensive. But I remembered what I'd done with the tube that I took out of this radio. I used it in the restoration of a Decca RP205 amplifier module quite a while back. And at the time I needed a tube, and I remember cannibalizing this particular radio to get that tube. So now it's come back. The tube you will see in operation is that actual tube that was on that Decca. So it's sort of time sharing for tubes around here, especially expensive ones. Enough waffle for now. Let's move onwards. So this is a setup. We've got a 1 kilohertz sine wave, 100 millivolts. Actually, I'm going to make it 20 millivolts to start. 20 millivolts RMS, and it's coming out of this channel. And I'm feeding it into the TA input, the phono or external audio input. The signal's going there. The negative or the ground is connected to the chassis, which is ground. I've got the TA selected here. That's off. That's TA. I've got the volume set to minimum. And I have the speaker output connected to the dummy load with speaker selected. And we're looking at, we'll be able to see the signal on the scope. I've fitted the ECC83 and the ELL80. Those are the only two tubes that are active. And I'm going to switch it on with maximum restriction. And we're looking at B plus over here. Now, if you recall, we needed 270 to 278 volts. It'll still be a bit high, or it can still be a little bit high because there are no other tubes. It's actually quite a bit lower because I've got quite a bit of restriction on there. But this is the way I want it right now because I want to see if the audio is coming through. So B plus is at 220 volts. It should be good enough to operate the tubes. And now I want to look at the scope. Now I'm increasing the volume. And I can hear it. And I can see it. And I'm going to change this to dummy load so we don't have to hear it. And there we go. That's maximum volume with a 20 millivolt input signal. Now I'm going to increase the level of the input signal. 30, 40, 50, 60, 70, 80, 90, 100. 100 millivolts. And we see that we've got some rounding off of the sine wave at the bottom there, and it seems to be doing it at the top as well. Let me drop the volume, and I'm going to increase the input level to 150 millivolts. And now we'll increase the volume, and yeah, it's actually clipping on the top and the bottom at about the same point, which means that the biasing isn't a problem. It's doing a good job there. What have we got? We've got, before clipping, or before that, we've got 3.8 volts RMS, and we can do the math and see what power that is. It's not that much. It's actually quite low. If I change this to 4 ohms, it drops that, and clipping happens a bit lower. I think it's more like 4 ohms. Now, with that flattening that we're getting, there's something else we can do. We can actually reduce the current limit, or the current limiting that's happening with the dim bulb tester. And that's what I'm going to do. I'm going to give it another light bulb. Now we're seeing 248 volts as B plus. Not quite 260 or 270. Let me give it another light bulb. And now the B plus is at 265. It's drawing 150 milliamps. Let me give it the last light bulb. That's almost no restriction. The radio is seeing 225 volts and it's seeing 270 volts B plus. And what do we have here? It's clipping at let's call it 4 volts. That's 16 divided by 4, that's 4 watts. Doesn't seem like much, does it? I bet you if we put the speakers on, it'll blow our ears out. That is a nice, nice sine wave. That is beautiful. So I think that's the end of another video. And I'm really, really happy with that result. It's a clean sine wave. That valve is by no means new. Neither the output valve nor the ECC83 are new. So I'm not quite sure how much difference a new valve in either of those positions would make. But from what I've seen here, I'm sure the result's actually going to sound pretty good. And because I want to put Bluetooth on this thing, I want this amplifier to be pretty good. I want to put a Bluetooth module at the end, as I do with a lot of these radios, much to the dismay and horror of the purists. Sorry about that, guys. Well, that's it for now. The next stage is I'm going to start going back on the radio, and I'll be looking at probably the AM next. So replacing the capacitors and checking the circuit on the AM part of the radio, which will then be followed by the FM part of the radio. And then, of course, there's still a lot of coming back to. We still need to come back and determine whether that guy is actually humming or not. We can't really see it I don't see much wobbling on the screen, but it could still have quite a bit of hum. I'll probably change it anyway. And also the selenium rectifier might need to come out. Now, that'll depend what I do with that selenium rectifier. I'm going to replace it, but whether I need a series resistor to drop the voltage or not will depend on what the final B plus is when I've got all the tubes working. So that's it for now, guys. Thanks for your company. I hope you've enjoyed that. If you have, share, subscribe, like, and all that jazz. And if you want to support the channel, you can do so on Patreon. The link is at the end of the video and also in the description below. Thanks for watching. Bye for now. Stay safe.